Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to calculate the average normal stress in an axially loaded bar. So let's take a look at what we're given. In the given information, we're being told to use the method of sections to find the average normal stress in each segment of the axially loaded bar. Then we're being told to state if the stresses are in tension or compression. So let's take a look at what we have here. In this figure here, this is our axially loaded bar, okay? And we see it's got two segments, A to B and then B to C. Now, why is it called axially loaded? Well, it's called axially loaded because all of the forces that are applied, we have 30 kips here and 20 kips here, are lying along the longitudinal axis of the bar. So whenever you have all of the applied forces in a system are passing through the long axis or the longitudinal axis of an element, we call that axially loaded. Okay, so that's the vocabulary word here, axially loaded. Now, why is that significant? Well, when you have a system that's purely axially loaded, that means that these individual elements will not be subjected to bending or rotation. Notice that because the 30 kips and the 20 kips pass through the longitudinal axis of this entire bar, you are not generating any kind of bending moments or couple moments. No rotations or no bending is occurring here. Only axial elongation or compression, okay? So that's the meaning of axially loaded. All right, now what about method of sections? Well, this is a topic we learned in statics. What does it mean? Well, in method of sections, we pass what we call a cut section through a member, and we look at one side of that member or that system. So we pass a cut section through a member somewhere, and then we isolate part of that member or a section of that member, and we apply equilibrium equations to that section. Okay, so this method of sections should be a review from statics. Nothing really new there. Okay, what else are we looking at here? Well, the cross section of member AB, that means what this member looks like on the inside of it, is a circle with a 2-inch diameter. And then the cross section of member BC, again, that means what it looks like on the inside, is a square with a measurement of 1/2 inch by 1/2 inch. So what is a cross section? Again, think of like looking inside of a member. So if you take like a cylinder, right? Like a bottle most bottles are cylinder shapes. If you look inside of a cylinder, what shape in 2D do you typically see? You see a circle of some kind, right? Or at least a ring, right? So that's what we mean by cross-section. What do we see on the inside of each of these members? All right, so let's go ahead and get started. We're going to write solution here, okay? And we are going to use method of sections, okay? So we're going to say by method of sections, and I'm going to abbreviate that MOS. I'm going to say pass a cut section through each segment of the bar, and we're going to do that one at a time. So you only do one cut section at a time, and again, that's from statics. So let's look at the first cut section through member BC. Okay, I'm going to make a cut through member BC, and I'm going to look at one side of that cut or the other. Does it matter if I look at the right side of where that cut is going to be, or if I make this cut here and I look at the left side? Does it matter which side I look at? No, it doesn't, okay? By method of sections, you could look at either side of what is happening on either side of a cut section, okay? So it's up to you. Now, I would choose to analyze the side that has the least going on or that's the easiest to deal with, okay? So let's do this. Let's say cut 1, and I'm going to say in member BC, all right? And so again, I'm going to make a cut somewhere in between points B and C. And then I'm going to say, let's analyze a right free body diagram, okay? And so when we do that, we've made a cut. I'm going to make this little cut symbol here somewhere in BC, all right? And I'm going to look at what's on the right of that, okay? So what's going to be left on the right? It's this little extension right here, okay? Now, what is happening there? Well, you're going to be able to see that 30 kips hanging off the end there, okay? Now, is the 20 kips going to be there? You might say, well, Dr. A, where's the 20 kips? Well, this 20 kips is being applied at point B, okay? And we have just made a cut somewhere in between B and C. So this 20 kips is to the left of that cut. The 20 kips is somewhere over here, okay? So if we're looking at a right free body diagram, we're not going to see that 20 kips, okay? Now we've made this cut here. Now what becomes visible? I'm going to change colors here, and we're going to have a normal force. I'm going to call this NBC, becomes visible there. Now, there are two other things that become visible here, okay? From statics, you might remember there is a shear force, we'll call that VBC, that becomes visible, and a bending moment, MBC, that becomes visible. Now, here's the thing. Because we know that this is an axially loaded member, and we only have applied forces like this 30 kips that lie along the longitudinal axis of the member, that means that there will be no shear force and no bending moment that show up there, okay? So when you have an axially loaded member, all you really need to draw in that free body diagram is the axial load that comes out of the cut section. In this case, that's a normal force in BC. And why is it called a normal force? Well, it's because it's perpendicular to this cut section, okay? So should we draw VBC and MBC here? Well, we can. And for the sake of completeness, sure, why not? But because this is axially loaded and you have nothing applied in the vertical direction or in the transverse direction, we know that the shear is 0 and the moment is 0. Now, if you want to prove that to yourself, you can say sum of the forces in the y direction equals 0. And if you just look at this free body diagram, the only force that has a y component is VBC. And so if that's the only thing with a y component and there's nothing else, then of course it must be 0. And then the same thing by taking some of the moments about the cut equals 0. You can come to a similar conclusion. MBC is also equal to 0. So again, for the sake of completeness, I'm drawing this because you should have learned that in statics. But because this is an axially loaded member, we know that these two are 0. And so you don't even really need to write that, okay? Now, the one that is not 0 comes from sum of the forces in the x direction equals 0, all right? And if you just look at this free body diagram, what do we write in the x direction? Well, we're going to say negative NBC plus 30 kips equals 0. And we rearrange this a little bit and we get NBC equals a positive 30 kips, which is in tension, okay? Now again, what does this mean? Okay, where did this negative sign come from? Well, remember, you have two sign conventions happening at the same time here with this equilibrium equation. One of them has to do with which direction you're talking about being positive and negative. So forces pointing to the right are positive, okay? So that means this 30 kips is showing up with a plus sign here. Forces pointing to the left are negative. That means that this NBC is showing up with a negative sign here because it's pointing to the left. Now you might be saying, well, hey, hang on, Dr. A, how do you know NBC is pointing to the left? Well, I really don't, right? Whenever you have an unknown force, you have to assume its direction, okay? Now, the orientation of it is pretty straightforward. The orientation of NBC is at 0 degrees. It's horizontal, okay, because it's a normal force, i.e. perpendicular to this cut section. But I'm assuming it's pointing to the left, okay? And when you assume an unknown force is pointing in a particular direction, You then perform the calculations of the equilibrium equation. That's what we did here. And if it comes out positive, that means that this force is, in fact, pointing in the direction that we assumed, to the left, okay? Now, it came out positive, all right? So it means it's pointing in the direction we assumed, to the left. Now, you might be wondering, well, wait a second, Dr. A, you just said NBC is pointing to the left, so there's a negative sign here, right? I did, but remember, I said there's two sign conventions happening here. One of them has to do with left being negative and right being positive, and that's reflected by this little notation above the summation, okay? The other sign convention has to do with what we are calling tension being positive or compression being negative, okay? So I am pointing NBC out of the cut. Notice NBC, the arrow is pointing away from the cut, okay? That indicates a tensile effect, okay? So that's the second sign convention, is what we call the sense of the force or the sense of the vector, okay? So I'm assuming NBC is going to pull on this cut section, which means tension. And when I do the calculations in my equilibrium equation, if my end result comes out positive, that means that NBC is in fact pointing in the sense that I assumed, which is in tension, which is pointing away from the cut, to the left in this case, and I can say that force is in tension here, okay? So again, all of this is statics at this point. We have not even done mech of materials. This is statics, all right? But this is just a review. Okay, are we done? No, we have two segments here, so we need to make another cut, okay? I'm going to say cut 2, and I'm going to say we're going to cut this one in member AB, okay? And then I'm also going to say the same thing. Let's analyze a left free body diagram, okay? And so now going back up to my original figure, I'm going to make a cut somewhere in between A and B. And remember, by method of sections, I could look at either a left or a right free body diagram. I'm choosing to look at a right free body diagram. So I'm going to look at everything to the right of where I'm making this cut, all right? So when I do that, what do I end up seeing here? Well, I've got this cut here inside of AB, and here's AB. And then here's BC, okay? Now, what forces are going to show up here? Well, my 30 kips that's being applied is still hanging out there. Now, this is where I see the 20 kips, okay? 20 kips is hanging out there because I've made this cut to the left of where that 20 kips is, all right? Now, if we want to be correct, we can also continue to include any dimension lines. We don't have any dimension lines here, but if you had dimension lines, you would put the dimension lines there because we have this entire segment showing up, all right? So what becomes visible here? Well, we have NAB, and then like we said before, we do have a VAB and we have an MAB, but what are those equal to? Well, they're both equal to 0. Again, you can look at it and see you have nothing in the vertical direction, so VAB must be 0, and you have nothing causing a rotation or a bending of this segment, so MAB is 0, similar to what we saw before. So here we're going to say sum of the forces in the x direction equals 0, and we're going to say minus NAB minus 20 kips plus 30 kips equals 0. Look at everything, all the forces in the x direction. We do some rearranging, and we're going to get NAB equals to what? Well, we're going to get 10 kips, and that is going to be in tension. Okay, how do I know that? Well, again, I solve for NAB, and I'm going to get 30 minus 20, which is 10 kips. It's a positive number. And because it's positive, it is the sense of that vector is in the direction I assumed here. I assumed NAB was pulling on this cut, creating a tensile effect. I did the calculations, came out positive. So it is in fact creating a tensile effect. And so we have 10 kips in tension in AB. Now, here's my question. Are we done with this problem? No. If we were in statics, we'd be done with it, but we're in mechanics and materials, right? So we've got to go one step further. The problem asks us to find the average normal stress, okay? What we found so far is forces, okay? So we have to do one step further. We need the average normal stress. So what is the average normal stress in member? I'm going to start with the first one I started with, BC, okay? Well, average normal stress is force divided by cross-section area, okay? So in this case, it's going to be NBC divided by the area of BC, the cross-section area of BC, all right? So this is going to be what? Well, the force in BC was 30 kips, and that was in tension. And the cross-section area, it was a square, so it's 0.5 inches squared, okay? Just a square shape. And so we're going to say 30 divided by 0.5 times 0.5. And I get 120 kips per square inch. Or we sometimes call this KSI, okay? So you could call this 120 KSI, and that is in tension. So that is one of my answers, all right? And then sigma AB, okay, that's going to be the normal force in AB divided by the cross-section area of AB, all right? And that's going to be 10 kips. And then what's the cross-section area of AB? Well, if we go back up, that was a circle with a 2-inch diameter, all right? So we just need the area of a circle. So I'm going to say that's pi d squared over 4. All right, that's the area of a circle. And when I crank this through, let's see what we get. Let me erase this real quick. It's pi d squared over 4. I'll just go ahead and put the 2 inches in there, 2 inches squared over 4, right? So that's easy enough. The 2 squared and the 4 cancel, so it's really just becomes 10 divided by pi. So here I get 3.18 kips per square inch, or KSI. Okay, so that is it. That is the conclusion of this example. We're going to have a couple more similar to this to really make sure we have a good understanding of this. But if you found this helpful, please hit like and subscribe, and check out the other videos on this similar topic. Thanks for watching.